Welcome to Applied Statistics, Module 4. We're going to be talking about hypothesis testing. So in statistics, I've mentioned before that the inference we do on the population is going to be either inference of estimation, trying to estimate parameters, or a related task, but not exactly the same, would be decision making, trying to conclude something about the population, specifically about the population parameters. We're going to frame these decisions in this way. We're going to have a null hypothesis, which is what we have assumed to be true, and we are trying to prove, or our goal is to prove the null hypothesis incorrect. If we do anything, that would be the task at hand. So, from a legal perspective, the null hypothesis would be that the accused is innocent, and the goal of the prosecutor is to get the jury to reject that hypothesis in favor of the alternative. So we call this alternative hypothesis, and it's the one and only alternative we are testing in a hypothesis test. So we only are testing between two possible hypotheses. And so we're going to, the process in all hypothesis tests goes like this. We state clearly what the null and the alternative hypotheses are. We collect some data, calculate what we call a test statistic, some useful statistic from this data, which will help us make the decision. And then based on a decided significance level, we're going to make a conclusion. So essentially, does the evidence presented to us from our collected data, encapsulated in the test statistic, is that strong enough to get us to reject the null hypothesis? Okay? So we really, we're going to be looking primarily, at least in this module, at tests of two parameters, either the population mean or the population proportion. So mu or p. In all of the cases we're going to be considering, the null hypothesis, we're going to use the notation h with a subscript 0. It's read h naught. Naught is the fancy English word for 0 or nothing. H naught. And it's called a simple null hypothesis because the null hypothesis will say that the parameter is equal to some prescribed value. So for example, h naught says the mean is equal to 15. In some courses, the null hypothesis might be have a less than or equal to or greater than or equal to sign. We will not be looking at that in this course. Technically speaking, a null hypothesis can be of any form, but it's not going to be covered in this course. So we're going to be looking at simple null hypotheses. And the reason is we need to know if under the null hypothesis, we need to have a specific probability distribution for the test statistic that we calculate. Remember, statistics can be considered as random variables which have associated sampling distributions. And so if we know the sampling distribution of the test statistic, we can say how likely or unlikely some value of the test statistic is. And that's the crux of the whole thing. All right, so the null hypothesis is h naught. The alternative hypothesis, in some courses, you'll see h1, h capital A, h lowercase a. In this course, I think you'll be seeing the first two interchangeably. I'm going to use h1, but just note it's simply a matter of notation, and there's no consistency across statistics courses, unfortunately. So h1. There are three types of alternatives: a left-tailed alternative, a right-tailed alternative, and a two-tailed alternative. So the left-tailed alternative says that the mean, instead of being equal to 15, it's, say, less than 15. A right-tailed would say it's more than 15, and the two-tailed is accommodating for both of those possibilities. So we say not equal to 15, either greater or less than, but just not equal. Which alternative hypothesis we choose you'll be presented with lots of word problems, will always be determined by the hunch or what kind of test the researcher is trying to do. If it says the researcher suspects that the mean has decreased and is now lower than 15, well, then we do a left-tailed test. If instead it says the researcher wants to know if the mean is different, the word different means not equal to, so we choose a two-tailed test. So you have to read carefully to determine which type of test. Okay, here's an example to give you a little bit of intuition about this process. So suppose that the average wait time at DMVs across the country is 70 minutes, and I just made that up. A new system is put in place at the local DMV to speed things up, and a random sample of wait times is observed. Now, the null hypothesis will be that the mean is still equal to 70 at this DMV. For the alternative hypothesis, we're going to choose mu less than 70 because we put the system in place to speed things up, meaning we want to test if the new system makes the average wait time lower than 70. All right, we're not interested in greater than 70. We're only testing if it's lower than 70. And so it stands to reason that the statistic we would want to calculate is going to be based on on the sample mean, right? We observe a random sampling of wait times from customers, and we calculate a sample average. And if the sample average is a lot smaller than 70, we would reject the null hypothesis. We would say, oh, the wait time is decreased. But the question is, how much smaller than 70 does the sample mean have to be? X bar is 69 small enough? Does it have to be 60 minutes or 50 minutes? And it turns out it really depends on how sure we need to be of our decision, and what we're going to call a significance level. Also, it depends on the sample size, and it depends on the standard error, which is like how much variability there was in our sample. All of these factors go into it to determine how much smaller than 70 does it need to be. And we'll get into that in more detail a little bit later. Okay, so first, when we make our conclusion, we really make it in one of two ways, and these are really what you want to be getting used to, and you'll see these in the homework again and again. So if the evidence in favor of the alternative, H1, is strong, we say we reject the null hypothesis, and there is sufficient evidence to support H1, the null hypothesis, or the alternative hypothesis. If the evidence in favor of H1 is weak, we'd say we do not reject we don't reject the null hypothesis, and there is insufficient evidence to support H1. So notice we're framing this all in terms of whether we reject the null or we don't reject the null. We're not saying we accept the null or we've proven the null to be true. That's not the way the null hypothesis works. The null hypothesis is just the best hypothesis we have yet. It just hasn't been disproven yet. It's very much the way that scientific theory works. The best theory that they have so far is the current theory, and it can only be disproven. It can't be proven true. Okay? So we're never going to make a conclusion, say we accept the null hypothesis. We really just say we don't have enough evidence to reject it. So I know it's kind of a weak statement to make, but that's the fact of the matter. In some stats courses, they don't make that point about that. They'll say, oh, you can just say accept the null, reject the null. I'm not going to, there are kind of philosophical reasons around that. But notice we don't say we reject the alternative. We accept the alternative. That's not exactly what we're doing. It's all in terms of the null hypothesis. So, of course, you can make errors when you do a hypothesis test, which is to say that sometimes your decision, although statistically done correctly and by the book, because of just the randomness in sampling, happens to not coincide with reality. So we're going to look at kind of this kind of cross-section, this table. In reality, the null hypothesis can either be true or it can be false. It can be not true. And our decision can either be to reject the null hypothesis or to not reject it. And of course, if we want to reject the null hypothesis if it's not true, and we want to not reject it if it is true, right? Those are both would be the correct course of action. But the errors are called type 1 and type 2 errors. So if the null hypothesis is true, but our sample leads us to a test statistic which causes us to reject it, so rejecting the null hypothesis when in fact it is true, that's called a type 1 error. And failing to reject the null hypothesis when it is not true and we should have rejected it, that's called a type 2 error. And in statistics, we put a limit on the likelihood of making a type 1 error. We call that our significance level. And we usually are going to use a significance level of 5%, 0.05, which means if the null hypothesis is true, there is no more than a 5% chance that we reject it by accident. All right. So, and if you feel like rejecting the null hypothesis is a really, really bad thing, then maybe you want to lower that significance level to 1% or even lower. But if you're not too concerned about rejection, if it's not life or death, maybe you can raise your significance level to like 10% or something. So the bigger the significance level, the easier it will be to reject the null hypothesis, but you're going to possibly be making more type 1 errors. So then the general scheme of things is we have two methods of doing hypothesis testing. The first is the so-called classical approach, and it goes like this. Of course we've collected our data and we calculate a test statistic, and we want to determine what our significance level is. It's often going to be given to you in the problem. So say it's given at 0.05, and this is the probability of rejecting the null hypothesis when the null hypothesis is true. Then we're going to calculate a rejection region or a critical region. There are synonyms, so they really mean the same thing. And depending on whether it's a one-sided test, a left or right-tailed test, or a two-tailed test, our rejection region is going to be either one tail of a normal curve or a t-distribution, or it's going to be both tails together. But the idea is that the total area of the tails in our rejection region or regions, that total area should add up to the significance level. Okay? And then the rejection regions are going to be kind of bounded by what we call critical values. So that's why they're often called critical regions with critical values. They're not called rejection values. They're critical values. That's consistent across all texts. So you get a couple critical values, and then if the test statistic is within the rejection region, or if it's beyond our critical value, we reject the null hypothesis. So this critical value is going to be determined by the choice of a significance level and what type of test we're doing. Okay? Also, it'll depend on degrees of freedom if it's a t-distribution. But don't get too worried about that, because all of this stuff can be done very easily using software. And I do all of those examples in the StatCrunch video, which you can watch next. So the alternative sort of method, which really is just another way of doing the exact same thing, is called the p-value approach. And so instead of getting rejection regions, what we do is we take our test statistic and we calculate a probability. And that is, if the null hypothesis is true, that gives us a probability distribution for the test statistic. So we assume the null hypothesis is true. Then we find the probability that the test statistic would be more extreme than the test statistic that we actually observed from our data. So it's possible that your sample data could have more extreme individuals in it, and you calculate what's the probability that it would result in a more extreme test statistic, that probability is this shaded area in the tail, or it would be in two tails if it was a two-sided test. That probability is the p-value. Okay? It's not, so p-value is not the same as that p is not proportion. It's not the p that stands for population proportion. You should think of the p as plausibility. That's what I think you should think of p as, the plausibility value. It's how plausible is the null hypothesis given the test, given the test statistic. How plausible? If the p-value is small, if it's less than alpha, we reject the null hypothesis. So a small p-value, a small, what I call a plausibility value, means unlikely, null hypothesis, rejected. A big p-value, we do not want to reject the null hypothesis. Okay? Now, there's something else that you'll see in the homework. It is trying to make a decision using a confidence interval. What I like to say is it's a little bit like hammering in nails using a monkey wrench. It will work, but that's not what a monkey wrench is designed for. So you can make a hypothesis test using a confidence interval work in the situation where you're doing a two-tailed test, and you have a significance level. Okay, so you have a null hypothesis, mu equals some number. I'll call it mu naught, some number. Think of mu naught as being some fixed number that's given to you in the problem, like 15 or 20, whatever number it is, 73 pounds. And the alternative is that mu is not equal to mu naught. So instead of getting a test statistic and doing all that, we instead construct a confidence interval. So you take your alpha level, say 0.05, and subtract it from 1, and then multiply it by 100%. So that turns a 0.05 alpha level, a significance level, into a 95% confidence interval. So we've done this a few times, and you see these kinds of the alpha and the confidence level, they go hand in hand. So our conclusion is, if this value mu naught lives outside our confidence interval, we would reject the null hypothesis, right? So those are the concepts. Now you should watch the StatCrunch examples, or the homework examples in the next video, and you'll get a sense of what you're actually going to be doing in practice.